Hey everybody, today's topic, actually a couple of random topics, not random, and they connect to the unit, but they don't really connect to each other, 10.6 and 10.7. Solving radical equations and then some formulas. Two of the formulas, I totally get why they're in this unit, because they connect to radicals, but one of them doesn't. I think maybe the editors, or authors, of the text didn't know where else to put it, so there's a bit of randomness to some of the formulas that we're going to look at, but nonetheless we'll get through those. But we're going to start by solving radical equations. So most of our focus for the unit so far has been with expressions, although we looked briefly at functions, but now we're going to look at solving radical equations. So first of all, what does it mean for an equation to be a radical equation? So if we're looking at this first example here, do you think that that is a radical equation? Well, just because it contains a radical doesn't make it a radical equation, so this is actually not a radical equation. This is not a radical equation. How about the next one? Do you think this is a radical equation? And it contains a radical, but not a radical equation. So this is not a radical equation, but the third one is. So this is a no. This is a no, and this is a yes. This one is a radical equation. Now what's different about this third one versus the other two is not just that it has a radical, but that the variable is underneath the radical. So a radical equation is an equation in which the variable is underneath the radical, okay? Now solving a radical equation, not so bad. Let me take you to my scratch paper for a second. If you were solving an equation like, let's say 2x plus 1 equals 9, we know how to solve this. We would subtract 1 from both sides to say 2x equals 8. We would divide both sides by 2, and we would say x equals 4. No big deal, right? A radical equation works in almost the same way. There's just going to be an extra step. So instead of trying to get x by itself, maybe you're trying to get a radical x by itself. So if our equation looked like this instead, we still have a times 2, we still have a plus 1, we still have an equals 9, we still have an x, but now the x is in a square root. Okay, we still want to get the square root of x by itself just like we would get the x by itself. So we would still start this by subtracting 1, and then we would have 2 square root of x equal to 8. We would still then divide both sides by 2, and now we have square root of x equal to 4. Now here we're done because x is by itself. Here, we still have one more step. If we're trying to solve for x and there's a square root over it, we have to get rid of that square root. So opposite of plus 1, minus 1. Opposite of times 2, divide 2. What's the opposite of taking the square root of a number? Right? If I had the square root of 81 to get 9, what would I do to the 9 to go back to 81? Well, I would have to square it, right? So in the same way, positive, negative are opposites, multiply, divide are opposites. Square rooting and squaring are opposites. So at this step, I have one extra, or at this phase, I have one extra step, and that is to square both sides. So subtract from both sides, divide both sides, now it's square both sides. So the square and the square root will cancel, which means we would have x now all by itself equal to 4 squared makes 16. And so our answer would be 16, and pretty easy to check that, right? If I put the 16 back in here, the square root of 16 would be 4. 4 times the 2 would be 8, plus the 1 would take me back to the 9, okay? Now what if at this step, what if we got the radical by itself, and instead of being a square root of x equal to 4, what if it was a cube root of x equal to 4? Well, then how would we get rid of a cube root? We would cube both sides, so then x would equal 64. Or if it was a fourth root of x equal to 4, then we would raise both sides to the 4th power. So then x would be equal to 256, okay? So we're trying to get the radical by itself, and then we're trying to get rid of the radical by raising both sides to the power of the index. Now sometimes that is the last step, squaring or cubing or fourthing both sides, but sometimes there's a little more to it. So let's say that the times 2 and the plus 1 were underneath the radical with the x. So if the 2x plus 1 was all underneath the radical, then this equation would have to start differently from the others. So this isn't really a plus 1 on this side. It's underneath the radical, and it's trapped there, and so is the times 2. In this particular equation, we would have to get rid of the square root before we could do anything else. So we would have to start this one by squaring. So a 2x plus 1 would then equal 81. And then once the radical is gone, the 1 and the 2 are no longer trapped. Then we could continue to solve for x. So 2x would equal 80, and then we would divide and we would say, okay, x equals 40. Okay, so back to our notes here. If we're going to solve a radical equation, the goal would be to isolate the radical. Okay, isolate the square root, the cube root, whatever it is, get it all by itself. So anything outside of the radical, like a ×2 or a +1, is going to have to be moved. Once the radical is by itself, we get rid of it. And we get rid of the radical by raising both sides. So by raising both sides to the power of the index. So if we have a square, we're going to square root, we're going to square both sides. If we have a cube root, we cube. If it's a fourth power or fourth root, raise both sides to the fourth power, and so on. And then some of our equations will be done at that step, but if x still isn't alone, we may have to continue to solve for x. Okay, and now we really have to be careful with our even roots here. Now I don't know if you remember when we solved rational equations. Let me go back to my scratch. Remember when we solved rational equations? Let's say we were solving like 2 over x plus 1 and 3 over, I don't know, x minus 4. We said there were two values of x that were restricted. What could x not be in this particular equation? Well, it couldn't be -1 because it would make a 0 in the bottom of that fraction. And it couldn't be 4 because 4 would make a 0 in the bottom of that fraction. And then if either the -1 or the 4 occurred as a solution, we couldn't actually count it as a solution, and we called it extraneous, right? So we have a similar concept happening here. Anytime we have a restriction, we have the possibility of having an extraneous solution. Well, restrictions are definitely something that happen with square roots, because there are certain numbers that we can't take the square root of, right? So if I had like the square root of x equal to, let's say, a -4, is there any way I could square root a number and get a negative? It's not possible, right? If I took the square root of 16, I'm going to get 4. If I try to take the square root of -16, that doesn't exist, right? Those are the only two things I could think of to try to get to this. This can't happen, because anytime you square root a number, right, if it's square rooting a number, it's got to be a positive number. Well, once in a while, you solve, using correct steps, solve a radical equation with an even root, and you get one of these answers that makes this thing not work. Okay, anytime you have the possibility, or you have a restriction in your equation, something that's restricted, like you can't have 0 in the bottom of the fraction, or you can't have a negative under a square root, then you have this possibility of extraneous solutions occurring. So we have to really be careful with our radical equations with even roots, because they can have extraneous solutions. And sometimes it'll be pretty clear when those are going to happen, but sometimes not so clear, so you're just going to want to make sure you check your answers, okay? So let's look at number 1. We want to get this radical by itself, that's step 1. So I'm going to start by adding 1 to both sides. So if I add 1 to both sides, that cancels. That would leave me 3 square root of x equal to 6. And now I want to get rid of the 3. It's being multiplied, so I'm going to divide it on both sides. That cancels. And now I have a square root of x equal to 2. Right, now I can get out the radicals by itself, I can get rid of the radical, and to get rid of a square root, I square both sides. So the square and the square root cancel, meaning x is all by itself, equal to 2 squared is 4. So x equals 4 is our solution, and I wouldn't do this every time on paper. You can do this in your head, but just so you can see if you wanted to check your work. Plug the 4 back in. If I put in 4 in for x, does this make a true statement? Well, the square root of 4 is 2, and 3 times 2 is 6, and 6 minus 1 is definitely 5. So if you end up with that true statement, you verify that that is the correct solution. Okay, and that can be done in your head. I just wanted to show you on paper. All right, so now we have the same operations happening in number 2, but the 3 and the 1 are now trapped in the radical. So our first step here is going to be to get rid of the square root by squaring both sides. So that allows me to bring down the 3x minus 1, and it's equal to 5 squared, which is 25. And now that the radical is gone, I can move the plus 1, or the minus 1 with a plus 1. So those will cancel. That leaves me 3x equal to 26. And now I can get rid of times 3 with a divide 3. So that cancels. X is by itself equal to 26, doesn't divide by 3, and this doesn't reduce. So we're left with this fractional answer. Okay? And if you wanted to plug it in, check it, it would work. And also, if you don't want to plug in by hand, you can use your calculator or Desmos to do this. So let's put in the square root. 3 times, so I'm going to plug in 26 thirds, and then if I subtract 1, that's where the equal sign is. That's where I stopped typing, and I could see in the corner here that it's equal to 5, which is what it's supposed to be. So you can use your calculator to verify if you don't want to do that by hand. Okay? All right, number 3. Got to get this radical by itself. That is step 1. So I'm going to start by subtracting the 2 from both sides. That's gone. And now I have 5 times my square root of x minus 4 equal to 10. Now I can get rid of the times 5 by dividing both sides by 5. That's gone. So now I have my square root of x minus 4 equal to 2. And now that the radical is by itself, I can get rid of it. So I'm going to get rid of a square root with a square. So the square and the square root will cancel, which means the radicand, the x minus 4, comes down. And then it's equal to 2 squared, which is 4 on this side. And now since x isn't all by itself, I have to take one more step of adding over the 4. So that cancels, and x is equal to 4 and 4 makes 8. Okay, and just to verify, that's 2 plus the square root, 5 times the square root of, instead of x minus 4, 8 minus 4, and that does in fact equal 12. Okay? Alright, so here we go. One for you to try. If you want to give it a shot, feel free to pause and try it out. Otherwise, working along with me here, I'm going to start by subtracting the 5 from both sides. So this is a negative 1 times my radical equal to 2. Now I'm going to divide that negative over. That cancels. And now I have my square root of x plus 1 equal to a negative 2. So now I get rid of my square root by squaring both sides. So x plus 1 comes down, negative 2 squared, negative 2 times negative 2 is going to be positive 4. And then I go to subtract the 1 over, and x equals 3 is my answer. Now I'm going to check this. If I put in 5 minus the square root of 3 plus 1, I get 3, and I'm supposed to get 7. Which doesn't mean I made a mistake. It means that that's possible. Sometimes we make mistakes, but I didn't here. What it means is this is an extraneous solution. So we got one solution here that doesn't work. If the one solution we have doesn't work, that means that this equation has no solution. Now, I would argue there's a point in the process where you should have known that that was going to happen. And it's where I knew I would have stopped working, and that would have been right here. If you have the square root of something equal to a negative, can you ever square root something and get a negative result? This is what I showed you a few seconds ago or a few minutes ago on the scratch paper. There's no way that can happen. So at this point right here where my square root's all by itself equal to a negative 2, I know this isn't going to have an answer. So if I saw that, I would stop because I know the answer I get is going to be extraneous. So square roots can't be negative. Okay, or fourth roots or sixth roots or any even roots. Even roots can't be negative, so I knew that this was not going to have a solution. So this is one of the cases where you can tell that you're not going to have an answer. There will be some where you can't tell, and you'll see one in a little bit. But there it is, okay, one with an extraneous solution. And since the only solution we got doesn't work, that means that equation does not have an answer. And again, that's because square roots or even roots can't be negative. Okay, so all square roots so far. Let's try a different radical. Same steps. Let's get the radical by itself. Let's divide the 2 over. That leaves us a cube root of x minus 3 equal to 1. And now we're still getting rid of a radical, but it's a cube root. So we get rid of a cube root by cubing both sides. So now the cube and the cube root cancel, so x minus 3 comes down, and 1 cubed is 1. Now we can continue to solve for x. Now we can add that 3 over because the radical is not got it trapped anymore. So x is equal to 3 and 1, which makes 4. Now, still a good idea to check your work, but odd roots, those aren't restricted the way even roots are. Remember, we could take a cube root of positive 8 and get 2, but we could also take a cube root of negative 8 and get a negative 2. The only issues we had were with even roots. So if it's an odd root, we don't have to worry about an extraneous solution. We will always get a solution. With an odd root, still a good idea, again, to verify it, but we don't have to worry about it being extraneous. So this will tell you if you, find my nth root, so a cube root of 4 minus 3. This will tell you whether or not you did the problem correctly, right? If you got something that didn't match up, it means that you made a mistake in your work, because there aren't extraneous solutions for odd roots, only with evens, right? Because evens are the only ones that are restricted. Now, number 5 might look a little more complicated because we have radicals on both sides, but in fact it isn't. Both of those radicals are alone. So we're going to start by raising both sides to the 5th power, and then both of those radicals go away. So we're really just solving 3x plus 4 equals 5x minus 6, and we want to get our like terms together. So I'm going to subtract 4 from both sides. That gives me 3x equal to 5x minus 10. Now I'm going to subtract 5x from both sides. So now I have 3 minus 5 is a negative 2x equal to negative 10. And now I'm going to divide both sides by negative 2. And that gives me x equal to that gives me x equal to positive 5. So x equals 5 is our solution. Now, I don't have to worry about it being extraneous, but if I want to verify it, let me type each side in. So I'm going to go into a 5th root of 3 times 5 plus 4. And let me type in the next one, the 5th root of 5 times 5 minus 6. And there it is. We get the same decimal in both of those, which means both sides are equal, and that's a verification that is the correct solution. Okay? Now, this is going to get significantly harder in number 6. Maybe you can see a difference between this one and the others. If you can't see it, the difference here is not only do we have a variable underneath the radical, but we also have a variable outside of the radical. And that's going to make this a different equation to solve once we get rid of our square. Now, the steps are the same. We want the radical to be alone. It is. So we're going to get rid of the square by squaring both sides. But we have to make sure on this side, on the left, not an issue. On the right, we have to make sure we are squaring the entire side. So that means 6x plus 13 can come down. That's no big deal. But on the other side, it means we have to multiply a 2x plus 1 by itself. We have to square it. So 6x plus 13. Over here, 2x times 2x is going to give us a 4x squared. Then we're going to get a plus 2x, another plus 2x, and then a plus 1. And this is a different type of equation that's resulted here. Now we're trying to solve remember what a square is? A quadratic equation. And we solve that a little differently than a linear equation, right? We're not looking for one solution. We're not trying to get 1x by itself. If it's quadratic, then we're going to try to solve by factoring. So the goal is to get a 0 on one side. So I'm going to subtract these two terms over. Subtract over the 6x, subtract over the 13 to 0 this side out. So 0 is going to equal, I got a 4x squared, 2 and 2 is 4, minus 6 is going to be negative 2x's there, and then 1 minus the 13 is going to be a negative 12. And now we're going to try to factor. First, let's take out the GCF of 2. That gives us 2x squared minus x minus 6. And then using bottoms up here, let's see, negative 12. Factors that make negative 1 would be negative 4 and 3. Dividing those by 2 means this becomes 2 times x minus 2 and 2x plus 3. So then we get two solutions. This tells us x equals 2 is a solution, and this tells us x equals negative 3 halves is a solution. Now this is one of the cases where we're not going to be able to tell if we have anything extraneous. It's possible that both of these solutions work. It's possible that neither one of them works, or it's also possible that we have one that works and one that doesn't. So we have to verify both. And if you don't want to do it by hand, use a calculator. So I'm going to go ahead and use my calculator. So I'm going to try the 2 first. I got to plug each side of the equation in separately and make sure they end up being the same thing. So I have the square root of 6 times 2 plus 13. That's 5. On the other side, 2 times 2 plus 1 is 5 again. So 2 is verified. 2 is a valid solution. Now I'm going to try this with the negative 3 halves. Now I'm just going to go back in here, delete out the 2 and type in negative 3 halves. And then I'm going to go here, delete out the 2 and type in negative 3 halves. And notice I have a positive 2 on the first result, negative 2 on the second result. Those two things are not equal, which means negative 3/2 is not a valid solution. So I verified with my calculator that this is extraneous and the other one works. So even though we got two solutions, we're not going to count the extraneous solution. So our only valid solution is x equals 2. Okay, so verify with your calculator. This is a lot easier than doing it by hand. And that is probably as difficult of a problem as you're going to see here. Now, fortunately, if you were, let's say, taking a quiz, which I don't know how many quizzes we're going to have for the remainder of the semester, but let's say you were taking your final exam, it would be multiple choice. And even if I knew how to do all this work, if these things are sitting there as multiple choice answers that I'm going to have to plug in to verify anyway, I'm going to use the multiple choice to figure out what my answers are. Okay, so this is work you should be able to do, but don't freak out too much if it feels a little bit harder than the other ones. All right, so number 7. This problem definitely looks different from the others as well. However, hopefully remember a property we talked about a few lessons ago, where we could take something like n to the, 2/5 power and rewrite that in radical form and say this is the same thing as a 5th root of n to the 2nd power. So a 5th root of n squared. That's the same concept here. So even though this rational exponent makes this equation look different, this is really just a cube root of this base to the 1st power. So this is equivalent to the cube root of 2x plus 1 to the 1st, which isn't going to change the 2x plus 1. So we're really getting rid of the 1/3 power in the cube root the same way. We would be cubing both sides. So that's going to give us a 2x plus 1 equal to negative 5 cubed is negative 125. Then we're going to subtract the 1 from both sides, giving us 2x equal to negative 126. And now we can divide both sides by 2. That cancels, and we have our solution. Negative 126 divided by 2 is going to be negative 63. And if you want to verify it with your calculator, not a bad idea. Although we don't have to worry about it being extraneous because it's an odd root, and odd roots will not have extraneous solutions. Okay? Same thing here. Now be careful when you rewrite this one. The 1/2 power applies only to the x. So the 3 is a coefficient, it's got to stay a coefficient. This is really 3 times the square root of x to the 1st. So 3 times the square root of x to the 1st. And then we have a -2 and an equal 7. So make sure the 3 and the -2 are not in the radical. The 1/2 power does not apply to those terms. So we start this by adding 2 to both sides. That gives me 3 times the square root of x equal to 9. I'm going to divide both sides by 3. And that gives me a square root of x equal to 3. And now I get rid of the square root by squaring. So I end up with x equal to 9. And that's going to be a valid solution. We plug it back in and use your calculator if you want. We have 3, and then we're putting in a 9, and we want to raise it to the 1/2 power. 1/2 power. And then if I subtract 2, better give me 7, and it does. Okay, so calculator can verify that for you. All right, one for you to try. If you want to pause, give it a shot. This is the same thing as a 4th root of x to the 1st. So a 4th root of x to the 1st plus 5 should equal 3. If I subtract the 5 over, we're going to end up with a 4th root of x equal to -2. Now I already know I can't take an even root, a 4th root of something, and get a negative, so I know that this isn't going to work. But if you didn't recognize it and you continued to solve, you would raise both sides to the 4th power. That would give you x by itself equal to a positive 16. And if you go to plug that in, let me show you. If you put in 16 raised to the 1/4 power, and then you add 5, you are not going to get the 3 that we have here. It gives you 7. So the calculator telling me that this is an extraneous solution. Now it's the only one we got, and it doesn't work. So since the one solution we have doesn't work, that means this equation has no solution. And again, if you recognize right here, that even roots, right, 4th roots, even roots, 4th roots included, can't be negative. Why does this look so ugly? Can't be negative. Okay, if you recognize it right there and you wanted to stop and say this isn't going to have a solution, totally fine. If you continue, you just got to make sure you verify because there's no way that 16 is going to work. Okay, so there's that. Solving radical equations. I know I went fast, but you can pause and rewind and watch again and slow-mo it or whatever you need to do. All right. Now 10.7, our next section is not really related to this, but somewhat related to our chapter. The three formulas that we're going to talk about here. Pythagorean theorem, I think we reviewed once already in our course. The Pythagorean theorem is a squared plus b squared equals c squared, and it's used to find the missing side of a right triangle. So right triangle, like the one pictured here, is a triangle that has a right angle, and in the right triangle we can call the legs A and B, and we call the hypotenuse C. So A and B, we call those the legs of the right triangle. They make the 90-degree angle, and C is the hypotenuse. The hypotenuse is the longest side. Now A and B, again, interchangeable. Doesn't matter which leg you call which. The two sides that make the 90-degree angle are interchangeable, but C has to be that longest side. It has to be across from that longest angle, right? The biggest angle. So across from the 90-degree has to be C, has to be the hypotenuse in terms of the formula, all right? So looking at number 1, we could call this A and B and C if we want. So we could say that A is some unknown, right? That B is 9, and we could say that C is 15 and plug into our formula. So we're going to go, I need more space here, so we're going to say that x squared plus 9 squared, or 9 squared plus x squared, those are the two that go together on the one side of the formula, right? Those have to equal, get rid of this, those have to equal, those squares added together have to equal 15 squared. So this is x squared plus 81 equals 225, and then if we subtract 81 from both sides, we kind of see how this is going to relate to what we were just doing. So we're left with x squared equal to 144. Now this is the reverse of what we just did. On the other side we had a square root and we got rid of it with a square. Well, now we have a square and we're going to get rid of it with a square root. So if I square root the square, x is all by itself. Oops, x is all by itself equal to, what's the square root of 144? It's 12. So our missing side would be 12. Okay. Same thing going on here. Square root of 9. Whoops, I'm missing a side. I'm missing two sides. No good. All right, well, let's say that this side here was supposed to be, I don't know, I'm just going to make something up. Okay, I'm not sure what happened to my side here, but there definitely needs to be two sides given and one unknown. So let's say that it's a radical 3. Okay, so these two sides are the legs, A and B, and then this is going to be C. So if I wanted to call this A, this B, and this C, or this B and this A and the other one C, doesn't matter, the legs are interchangeable. So we could say here that the square root of 9 squared plus the square root of 3, let's make it 2 square root of 3, just so I can show you how to handle that. Oops, I had to put an eraser on. 2 square root of 3 squared has to equal x squared. So the square root of 9 squared, that should be intuitive. The square root of 9 squared, square and square root are going to cancel, going to give you 9, right? But what's happening here in this next term, if you are squaring 2 square root of 3, that means you're multiplying 2 square root of 3 by another 2 square root of 3. That means you have a 4 on the outside and a radical 9 on the inside, or that you have to square both pieces. So 2 squared is going to be 4, and square root of 3 squared is going to be square root of 9. And that's going to be equal to x squared here. So then we have 9 plus, well, this is 4 times 3 here, and 4 times 3 is 12. So now we have x squared equal to 12 plus 9, which is 21. Now it's a little easier here. We know the square root of 144 is 12. Here, oops, we don't have a square root of 21, but that's okay. We use the same process. To get rid of the square, we take the square root of both sides. So we would say x is equal to, since this doesn't have an exact square root, let me move this over here. here, we're going to say x is equal to exactly the square root of 21, or we could say that x is approximately equal to square root of 21. So we can estimate with the calculator about 4.6. Okay, now if we were dealing with context, I would say the decimal would be more appropriate. Out of context, I would say the exact answer is the preferred answer. And if 21 was something we could break down, then we would definitely want to simplify there. Okay? All right, here we got another guy. If you want to try it out, feel free to pause and give it a shot. But this should be 3 squared plus x squared, or vice versa, equal to 4 squared. So 9 plus x squared equals 16. If we subtract the 9 from both sides, that gives us x squared equal to 7. And then we can take the square root to get rid of the square, and that gives us x equal to square root of 7, again, is our exact answer. Now, if that was a radical that can be broken down, we saw that earlier. If, let's say it was the square root of, I don't know, 28, right, where 2 goes in 14 times and then 2 goes in 7 times, and we would simplify it and say 2 radical 7. If it was a radical we could break down, we'd want to do that. But since the radical 7 doesn't simplify, that's going to be our exact answer. Again, we could approximate it if we were dealing with a word problem, it'd be more appropriate to do that, but the exact answer is going to be preferred when there isn't any context. Okay, so there's your Pythagorean theorem. And then we have the distance formula, which is basically where the Pythagorean, or basically something that comes from the distance, from the Pythagorean theorem. The distance formula, which says d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, can be used to find the distance between any 2 points that are on a coordinate plane or on a graph. And it is derived from, it comes from the Pythagorean theorem. Okay? And I actually don't like this formula, but I don't want you to go into the next class not having seen it before. I don't like this formula because I don't use it. I use the Pythagorean theorem, which is what it comes from. Let me try to show you what I'm talking about here. Like this. Okay, so if we were looking at a right triangle on a coordinate plane, so instead of just having a right triangle in space, if we put it on a coordinate plane, that means if we put it on a graph, how might it look? Let me just draw this out for you. Okay, so let's say that we had a triangle on this coordinate plane, and one corner was here, one corner was here, and then we put the other corner here. If I wanted to know the distance from this point, where the coordinates here, 2 and 1, 2, 3, 4, 5, 6, 7, 8, the coordinates here at 2, 8, and then I said I wanted to know the distance between that point and this point, which is at 3, 4, 5, and 2. Okay, if I wanted to know the distance between those 2 points on the graph, well, that's the same as finding the length of this side of the right triangle. So if I wanted to know the distance between these 2 points, it's just like using the Pythagorean theorem. If I wanted to know the length of this side of the right triangle, well, all I'm doing is going from 2 to 5 on the x-axis. And if I take the 5 and I subtract the 2, right, that would give me that 3 units of distance that we've gone. And on the y-axis here, I'm going from 2 to 8. So if I'm starting at 2 and I'm going to 8, if I subtracted the 8 and the 2, that means I'm going 6 units this way. 1, 2, 3, 4, 5, 6 units that way, right? So the distance formula says, take those 2 x values and subtract them, and then take those 2 y values and subtract them. That's going to give you how far you are here and how far you are here. So that distance squared plus that distance squared, well, that's supposed to equal our missing distance squared. And to get rid of the square, we square root. So if I just took the square root of both sides, then I'd be left with c here, and I'd have my square root there, and there's my distance formula. Okay, so it's really just Pythagorean theorem, but it's is trying to make it more general. Like if I could easily count that I'm going from 5 to 2 is 3 units or from 2 to 8 is 6 units, then it's no big deal to say that the distance here is 3 and the distance here is 6. But if there are numbers that are farther apart or you're dealing with positives and negatives, it's possible that the formula is a little easier for you to deal with. So I'm going to show you how I use the Pythagorean theorem and the formula, and you can kind of decide what you like better. Okay, so let me use the formula first. Some people just prefer the formula. This is our first coordinate, so we're going to call this x1 and y1 because it's the first x and the first y. Second coordinate, so x2, y2. So according to the distance formula, we're going to be looking at the square root of x2 minus x1. That's 2 minus a negative 1 squared, plus y2 minus y1 will be 1 minus a negative 3, and that gets squared. So this is 2 plus 1 in here, which is 3, and then 3 squared is 9, so this becomes a 9. This is 1 plus 3 here, which is 4, and 4 squared becomes a 16, and I have to add those. So I'm looking at the square root of 25, which is 5. So the distance between those 2 points on the graph is 5 units. Now if I was doing this problem, thinking about it in terms of the Pythagorean theorem, I know that the distance between the x's is this length of my triangle, and the distance between the y's is this leg of the right triangle, and what I'm looking for is c, right? So if I'm looking in terms of the Pythagorean theorem, A is how far am I from one x to the other x? So how many units is it from negative 1 to 2? That's 3 units. And then B is how far is it from one y to the other y? Well, from negative 3 to positive 1, that's 4 units. And then I'm just looking for C. So 3 squared and 4 squared equals C squared. That's 9 and 16. And that's 25, and the square root of 25 is the same 5 we got over here. That's just another way to think about that problem. So if that made sense, and I'll show you it again with the other, then you can use that. If you prefer to just plug into a formula, it's really up to you. Okay? Let me show you again here. Let's use the formula. So this is x1, y1, x2, y2. So the distance is going to be the square root of x2 minus x1 would be negative 1 minus 5 squared, plus y2 minus y1 would be 3 minus 6 squared. And so that's negative 6 squared, which is 36. That's negative 3 squared, which is 9. And when I add 9 and 36, I get the square root of 45. Now the square root of 45 is not exact, but that one can be simplified. 45 is 3 times 15, which is 3 times 5, so 5 can come out. So we're going to say this distance is exactly 3 radical 5. 3 radical 5. I don't know why I boxed that one in and not going to box this in and not the other, but there it is, 3 radical 5. Now, again, in terms of Pythagorean theorem, if you are understanding what I'm saying here, one leg of the right triangle, right, one of these legs and the other's legs, the distance between the x's and the distance between the y's. So if I'm looking for A, how far is it from 5 to negative 1? That's 6 units. And then B, how far is it from 3 to 6 is 3 units. And then C is going to be what I'm looking for. So 6 squared is 36, 3 squared is 9, and that's going to give me the same thing that I had on the other side, just for me a little easier to manage it that way than the other way. But you have the option. Okay, so I'm going to leave that there in case that helps you think through that, but you're welcome to use whatever makes sense to you. All right? Now those formulas make sense in this chapter because they deal with radicals. The midpoint formula has nothing to do with radicals, but I think there was no other maybe good place to put this formula. So it's in here, even though it doesn't connect to anything else we were doing. The midpoint formula, like it says, is used to find the midpoint between 2 points on a coordinate plane. So midpoint formula is going to be, it's giving us a point, it's giving us a coordinate, and within the coordinate, we have to add our x values and divide by 2, and we have to add our y values and divide by 2, which should make sense. If I was looking at, I don't know, on a coordinate plane, right? If you're looking at a point that's here and a point that's here, 2, 3, 4, 5, let's say 6, whatever. I want to know what's in the middle of those 2 points, and Okay, this is not a good picture. Let's try this again. Okay, like, let's just look at these two y values, for example. If I had a y value of 5 and a y value of 7, that means I'm looking at 5, 6, 7. What's in the middle of those two y values? Well, I can see that it's 6. Now, if you can't see it, if you can't just count it out, it's the average of the two numbers. You take the 7, you add the 5, and you divide by 2. And what's 12 divided by 2? It's 6. All we're doing is averaging these two numbers. Now, if you can look at the two numbers and know what's in the middle, awesome. If not, you add the two numbers and divide by 2. Okay, we're basically just averaging our x's and averaging our y's. What's in the middle of the x's, what's in the middle of the y's is going to be the midpoint for those 2 points. So it averages the x's and y's. Okay, so here, again, I don't really like the formula because this is common sense to me, but this is your x1, y1, this is your x2, y2. So the midpoint formula says add those x's, add 8 and negative 2, and divide by 2. Add the y's, and divide by 2. And if you add these x's, 8 and negative 2 is going to be 6. 6 divided by 2 is 3. And then if you add the y's, 7 and 5 is 12, divided by 2 makes 6. The midpoint between those 2 points is at 3 and 6. Okay? Now feel free to pause and try this one out. Otherwise, let's keep going. x1, y1, x2, y2. The midpoint here says add the x's and divide by 2. And then, sorry, going too fast. Add the x's, 3 and 2, divide by 2. Add the y's, 0 and 12, and divide by 2. So the midpoint is going to be equal to 3 plus 2 is 5, and 5 doesn't divide evenly by 2, so we can leave that as a fraction. 12 divided by 2 is exactly 6 again, so we're going to say the midpoint is at 5 halves and 6. Or if you wanted to make this a decimal, at 2.5 and 6, that would be fine too. Okay, either way. All right, so that's your midpoint formula. What we're going to do on this last page here is look at a couple of applications, trying to decide which of the formulas is going to be best to help us solve. All right, so in number 8, Brian biked 10 miles east of his house and 8 miles south from there. How far is he from his house? So let's try to draw this out. All right, here's Brian. He biked 10 miles east of his house. Let's draw his house. So let's draw Brian's house. Okay, if he goes 10 miles east, maybe he goes this way 10 miles. And then from there, from that point, he goes 8 miles south. So 8 miles south, and east and south are going to make a right angle. What we're looking for is if he started here and he ended here, how far is he from his house? We're looking for this distance. And we can absolutely use Pythagorean theorem to find that distance. So we're looking at 8 squared and 10 squared equal to, let's call the missing distance x squared. 8 squared is 64. 10 squared is 100. 164 when we add. And now we're going to take the square root of both sides. And there is no exact square root of 164. Now, if this didn't have context, I would say break that down. But even if we broke it down, let's see. If we were to break down 164, 2 goes in 82 times, and then 2 goes into that 41 times. We're not going to say that Brian is 2 radical 41 miles from his house. It just doesn't make sense to speak in radical. So even though that radical can be simplified, this is where the decimal approximation is going to be a better answer. So we're going to say that x is approximately the square root of 164 is about 12.8. So 12.8. So we're going to say he's about 12.8 miles away. Okay, not so bad. All right. The nearest Starbucks is 3 miles north and 1 mile east of GCC. If Linda is 5 miles east of GCC, how far is she from Starbucks? So I don't know about you, but when I'm looking at this, I'm seeing an ordered pair. 3 miles north, 1 mile east. So Starbucks, just to give us some reference here, is 3 miles north, 1 mile east. So the north and the east I'm going to put together like this. And then Linda she's 5 miles east. Okay, so east was second in my other coordinate, so I'm going to put east here again, 5. Now, if she's not north at all, what could we put in here for the north? Well, 0. She's only east, so she's not north at all, okay? Or think about this on a graph, okay? Think about GCC as like the hub, it's the origin. If Starbucks is 3 miles north, 1, 2, 3 miles north, and 1 mile east, we could give that a coordinate. And then if Linda is 5 miles east, 1, 2, 3, 4, 5, we could give that a coordinate, right? Or going the other direction. I actually kept everything positive here. Let's say that, let's call this, well, that makes more sense anyways, right? To call that east. I don't know why I went the other way. And north on a coordinate plane again, GCC is going to be the hub. So 3 miles north and 1 mile east would be there at it's 1, 3, it doesn't matter. And then 5 miles east, 1, 2, 3, 4, 5 would be a point here. Okay, so one of the points has to be zeroed out. And you are looking for how far is Linda. This is Starbucks. Okay, this is Linda. You want to know how far apart from one another they are. So you can do this one of two ways, as I showed you before. You can use the distance formula to find the distance between the 2 points, or you can use the Pythagorean theorem. Either way is going to get you the right answer. So let's do this here. x1, y1, x2, y2. Distance is x2 minus x1 is 0 minus 3 squared. y2 minus y1 is 5 minus 1 squared. So that's negative 3, but when you square it, you get 9. That's positive 4. When you square it, you get 16. And so we're looking at the square root of 25, which is 5. The same thing is going to happen here. Even though my coordinates are backwards from what I wrote here, I got 1, 2, 3, 4 as a length of that side, 1, 2, 3 as a length of that side, and then 3 squared plus 4 squared equals c squared. It's going to get us the same thing, okay? So however your brain is managing that. Hopefully it's managing in one of the two ways. Linda is 5 miles from Starbucks, okay? From Starbucks. Although Linda should be home right now because we're trying to stay home. Okay, Starbucks is only open in the drive-thru, so I hope Linda has a car if she's trying to get there. All right, last one. PQ is the diameter of a circle. Let's draw this out. Circle. Diameter of the circle. Hold on. Diameter of the circle, if you know what that does, it goes through the center and has endpoints on the circle. So a diameter might look like this. Okay, and it says that if PQ is the diameter of a circle, that means we're looking at, let me get rid of this, P being here and Q being here. Okay, P is at -2, 5, and Q is at 6, 7. And it wants to know what are the coordinates for the center of the circle. Well, I could draw this on a coordinate plane, but it doesn't matter. If we're looking for the center of the circle, we're looking for the midpoint of that segment. So for the midpoint, we add the x's, which would be the 6 and the -2, and divide them by 2. We add the y's, which would be the 5 and 7, and divide them by 2. So this is 6 and -2 is 4. 4 divided by 2 is 2. This is going to be 12 here, divided by 2 makes 6. So the midpoint of the circle is at 2, 6. Okay, so the center is at 2 and 6. All right. Now, I don't think on your homework assignment I gave you too many word problems. If I did, it might have been a 1 Pythagorean theorem problem. So hopefully, if this is a lot for you, it's going to be manageable when you get to your assignment. And then just as a heads up, we only have one more section to cover in chapter 10. So 10.8, which will happen on Tuesday,